Welcome. Today we are going to go over the virtual flying pig lab. And I wanted to start off by looking at kind of a picture of what the pig was doing as it flapped around in its circle. Here's my pig, and here is the circle that it went around in. I'm going to draw two different pictures of the same thing, showing the pig going around in the circle. And the reason for that is I would like one of them I'm going to label my forces on, measured in newtons. And the other one I'm going to label my lengths on, measured in meters. And so when we're setting up any of these problems for circular motion, we always want to have a nice force diagram. And so what you'll see is that, of course, everything has the force of gravity acting on it, and the pig's connected to a string, so it also has a force of tension. And when we're going in a circle, we know that we need to have an unbalanced force pointed inward towards the center of the circle. And so we see that we need to break the force of tension up into components in order to have a force pointing inward towards the center of the circle. But what we'll also see is that this force of tension y balances out the force of gravity so that the pig is not accelerating vertically, it's only accelerating inward. Just by looking at this force diagram, I can make some equations. I can say that Fty is equal to Fg, and therefore should be equal to mg. And this is actually what I'm trying to solve for, is g right there. And so what I need to do is find a different way of finding my Fty. Well, another force I can find would be my Ftx. And my Ftx is going to be my net force. It's my inward force. We can call it my centripetal force. And it's equal to m times v squared over r. I can solve for this Ftx if I know a speed and a radius. So my speed is going to be solved for by doing 2 pi r over t. And t, you had to measure. T is measured as taking the number of seconds you measured divided by the number of revolutions that you counted. So you had to time how long in seconds it took and count the number of revolutions. And so the value you plug in for your time period is seconds per revolution. But to find the radius of the circle, let's go back over to this other picture and say that to find the radius of the circle, you took a measurement. The measurement you took was a length measurement, and you tried to measure this value right here from end to end, which would be labeled as the diameter of the circle. And the reason we measured the diameter is that that's equal to twice the radius. And so we were able to find that radius by measuring that diameter. So we measured the time period by counting the number of revolutions in seconds. We measured the radius by doing the diameter divided by 2. And then we were able to solve for the speed and solve for the force of tension x by doing mv squared over r. Well, why do I care what the force of tension x is if what I'm really trying to solve for is the force of tension y? The answer is there's an angle in this triangle that can relate the force of tension x and the force of tension y. What we could do is we could say that the tangent of this angle is equal to the force of tension x over the force of tension y. And so really now, to solve for my force of tension y, it's going to be equal to the force of tension x over the tangent of theta. So I can find force of tension y knowing force of tension x and that angle. I need to find that angle. That angle can be found because they gave us the length of the string. And we know what the radius of this circle right here is. And knowing the length and the radius, what we're making is a nice right triangle right here, where the radius of the circle r and the length of the string l can be used to calculate this angle theta. So to find theta, I can say that the sine of theta is equal to the opposite, which is the radius, over the hypotenuse, which is the L. And so I'm going to solve for theta by doing the inverse sine of the radius over the length measurement. Now the reason I find theta again is so that I can find what FTY is by doing FTX over the tangent of theta. The whole goal of this lab is to find out what G is. We know it's 9.8, but we're trying to find like a different way of solving for G and seeing how we did. So because FTY is equal to FG, which is equal to MG, the other way we have of solving for FTY is to say that FTY is equal to FTX over the tangent of theta. What we want to do is say, okay, that means really that FTX over the tangent of theta, that's one way of saying FTY, is equal to M times G. That's another way of saying FTY. And so now we're going to solve for G. Once we've solved for G, we're going to compare it to our known value. When we find a percent difference, we're going to take our actual value of 9.8 and we're going to subtract the experimental value we got when we solved for G. And it's going to be the absolute value of that, divided by the actual value, 9.8. We're going to multiply that by 100% to find what our percent difference was from the lab and to see how good of a job we did solving for G, the acceleration due to gravity, by looking at a flying pig flying in a circle.